Yeah, so I'm going to talk about a new type of ADT called the queues. A queue is a special kind of ADT where items are inserted at one end called the rear and deleted at the other end called the front. This is a list which is first in, first out. Okay, and this is an ordinary queue. There are other types of queues that we will learn about called a priority queue, where elements are deleted based on their priority. But for now, we will work with the ordinary queue. So if this is the ADT queue, make null creates an empty queue. On queue inserts an element X into the queue. DQ removes an element from the queue. Front looks at the first element that is there in the queue. Empty tells you whether given queue is empty or not. Okay. And I'm going to use a linked list representation of queues. Just like I did for the list, what I'm going to do is I am going to create a dummy cell with an empty node which does nothing. So when I do an on queue, I insert it at the next to the dummy element. And so for example, when I'm inserting X, it inserts it next to the dummy cell. Then when I do an on queue of Y, it is inserted at the rear at the end of where X is, okay? So I have two pointers, front and rear, which initially point to the same dummy cell. DQ, for example, what do? I remove this particular element. Actually, the dummy cell will have the element X. And so what I have to do is I just have to move this pointer over here, or I move this pointer here, X will become the dummy cell over here, okay? So I can do this. I can do various, this is a sequence of queue operations that I have. And here is, I'm storing a simple example of queues with substrings. So I've created a recursive data structure where each node in the queue consists of substrings. And I have the see again that I have aliased position to a pointer to the node over here, a pointer to this particular node. And then I have, as part of implementation is in C++ again here, I keep a position front and rear, make null on queue front, DQ empty. On queue is essentially what we're doing is rear pointer next, I create a new element, save the new element over here, and rear pointer next equal to null. So you find the queue between the front and the rear. DQ, what do? Notice that I just get the next substring. I just update front. So actually the dummy cell now contains the first element which was there in the queue, but we're not going to ever allow to access it. Therefore, DQ is a simple order one operation, and so is on queue a simple order one operation. This is possible only because we maintain two pointers to the front and the rear of the queue. Okay, so there's a simple ADT for the implementation of the queue using a linked list. There are all operations are done in order one. So we talked about the linked list implementation of queues. Queues. Since queue is also a list, it can be implemented using an array tool. An array implementation can also be beneficial. Because one can prevent the queue from growing very long. So how do we perform an array implementation of the queue? So I'm just going to give you a sketch of this queue here, or let me call it ADT queue, and some array of some element type. Okay, and we have the same interface functions. Create an empty queue, check whether the queue is empty, on queue, on DQ, and can also do a queue full because it's an array implementation. Okay, I might do, as we saw, the queue has 2 pointers, front and rear. Okay, so how do I store this in a queue? So initially I'll have an array with front and rear with an empty queue pointing to the same position. Then what do? I insert an element into the queue. Let's say I do an on queue. X, this is front now, and this is rear. Okay. Then I can keep on queuing like this. Let's say I have X, Y, Z, W, R. This is front, this is rear. Suppose I DQ now. What will happen? Front will suppose I DQ. What will happen? X will be removed and I'll have Y, and this will be front. Okay, and this will still point to rear. But you already, now suppose I want to unqueue. It's already full. So what do? I need a mechanism. I want you to figure this out by which I can put something back here. Let's say I'm putting L. And now this would be the new rear. Okay. It'll be the new rear. Now, so I can keep doing this, and the idea of this is called a circular queue implemented using an array. I want you to think about it, how you will implement this. And the queue is found somewhere between front and rear over here. That's it. Okay. Now there's a problem with this implementation, because now let's say I have this situation here and I am on queuing one more element. Then what will happen? Let's say I'm adding M. Then what will happen? Rear is already pointing here. There's one element still, and front will also point to this. And you can say the queue is full. But we saw a while ago that front and rear pointing to was also an empty queue. Okay. So I want you to figure out how you will solve this problem. How you will solve this. Okay. And There are other underlying representations for queues. There are some nice problems like this. It's called a circularly linked list problem. I gave a pointer P, only one single point, no front and rear. How can I devise? And by the way, all operations on queues using arrays are big O of 1. Similarly, this is a circularly linked list with one pointer, P, and I want you to devise all queue operations using order 1. Okay, so take this as a simple assignment to do, and we'll stop here on queues. Yeah, we can also perform or can also define a queue ADT, just like we did the stack using the list ADT. And let's see how we'll do this. So I can define an ADT queue, and it has as its private part list ADT L. And we could also store front and rear, which are of type position as before. And we can write interface functions of this kind. Right? On queue, I'm sorry, before on queue, let's create a list. Let's say make null. And what we could do here is we create the list and say L dot make null. And we could further say front is L dot first, position of the first element, and last is, or rear is L dot end. I can write a make null like this. Then what will on queue be? Where we try to insert an X element of some element type. Clearly the rear is pointing to the end. So we'll do L dot inserter L dot, sorry, insert of L dot X comma N dot L dot. Remember, this is how we had the format of the list, X comma L dot end. Okay, and DQ will be to return the element. We'll say return, which is of element type, say L dot retrieve of L dot first, or first. I could just do this, sorry, first here, first front, sorry, front. Here too I can write rear because I'm making two pointers over here, and I can say L dot deleter front. Okay, and front will of course have to be updated L dot first. Okay, this can be the BQ operation, and empty would be L dot first equals L dot end, return true. Okay, and so on. So you can keep writing all the front would be what out of Q of L dot retrieve of L dot first, no deletion, just like we did for the top and the for stack top. Look at what is stack top and removing the element which is there on top, stack top. So this is what we have seen so far of ADTs called this stacks. Sorry, we started with basic arrays. These are the fundamental abstract data types that we have. Lists, stacks, queues, and we saw that each one of them is a special ADT in that specific operations are permitted. All these belong to that of the linear ADTs. Okay. We'll talk about other types of ADTs in the